Okay, so our next speaker is Colin Sterckx from Type. He's going to be telling us about black holes in Type IIB as well.
Okay. Well, thank you for the introduction. Thank you for being here. I want to tell you some new results we got recently with the collaborator Adolfo Guarino, Annick Rudra, and Mario Tridiante about black holes from Type IIB as faults. So we heard a lot about black holes already yesterday, but I still want to put them back in the center as an introduction to the results that I want to present to you. So the main star of the show are these universal black holes, and they're uplift in M3 and Type IIA. So these universal black holes, they are a solution of n equal to 2 supergravity, pure n equal to 2 supergravity in 4 dimensions. They are solution of this form, so you can see that you have like some kind of horizon here at r equal LEDS4 over 2, and when you go to infinity, this kind of matrix goes back to an ADS4 metric. These kind of black holes, importantly, they are supported by some fluxes. So here is the field strength of the R-symmetry vector fields, and you need to give them some magnetic charges to preserve supersymmetry. Okay, why do we care about these black holes? Because they have like some important properties. In particular, their entropy, by entropy I mean once again just the area of the horizon, is basically just related to this ADS4 radius up to this factor here, G, which is just the genus of this horizon of the black hole. Okay. So we care about them because we can test ADS CFTs with them. So they should be thought of as flows from some ADS4 to some ADS2 in the deep IR. And so they should be thought as a flow of CFT3 to CFT1s. So you put the CFT3 on some sigma G times S1, and you put some topological twist. And then you can compare data that you get from the ADS part to some computation you can do in the CFT part. So for example, you can compare the on-shell action and the black hole entropy, which are related to, the free energy and the topologically twisted index that you can access using some localization techniques. So really, you can do computation on both sides of the correspondence. Okay, so what are these CFTs here? CFT3, CFT1s. Well, it depends on how you are going to embed this 4-dimensional theory, this 4-dimensional n equal to 2 model inside of string theory. There are several ways to do this. Ways that we know how to do this are, for example, this M theory embedding. So you start with M theory 11-dimensional, you put it on a 7 sphere. You get some maximal supergravity with some SO8 gauge group. You do some extra reduction, and you get now an n equal to 2 model with 3 vector multiplets, and you can start building black holes there. And now the point is that this embedding of this n equal to 2 model in M theory is due to some ABGM CFT3, and you can compute topologically twisted indices here and check that everything is all right. You can do the same thing in massive 2A. So quickly, just you put it on this time S6. You get some different maximal supergravity in 4D. Once again, you restrict a bit more to some invariant sector. You get some n equal to 2 theory. These times with you need to keep some hypermultiplets. The gauge group is a bit different as in the previous case in the n equal to 2 model, but still you can study you can classify horizons in this model. You can find universal black holes again, and you can compare with the dual, which is this SUN Chen-Simon at level K in this case, and you can check that everything is all right. Okay. So here our point is that we are going to put now these black holes in Type IIB, which is like the new thing. So how are we going to embed these black holes in Type IIB? Well, first we have to start from 10 dimension, and we have to put it down to 4D. That's the first step. And the way that we are going to do this is by using this S-folding method. So we are going to compactify on a specific space, which is S5 times S1. And along this S1, we are going to put some monodromy using the SL2 Z symmetry group of Type IIB strings. And we are going to get some maximal supergravity in 4 dimensions with a very specific gauge group, and with this we can start looking for a solution for black holes to which we would be able to compute duals in the CFT side. Just as an aside, this whole thing of compactification, I've simplified it a bit. The framework that we're using all the time behind this when we are uplifting compactifying solution is exceptional field theory. I'm just like saying this so you know that it's been used, but I'm not really going to use it here in this talk. So it's just to let you know that this is really like the fundamental tool that we're using to do this compactification, and without it we could not do this. Okay, so we have this 4D maximal supergravity. Since this black hole goes from ADS4 solution at infinity and then comes to some ADS2, we first need to understand what kind of ADS4 solution we can have here in order to then make them flow to some ADS2 solution. And luckily for us, this has been already been done. So we have some families of n equal to 2 solutions. So this is this blue rectangle that you can see here. Which has some point of symmetry enhancement. So they're all like ADS4 solution that are parameterized by these two variables, phi and chi. And you have like one point which is n equal to 4 supersymmetric with an SO4 R symmetry group. There are some other n equal to 2 solution you can find here. And just as an aside, because it's swampland and not supergravity, I just want to let you know that there is also like extra deformation of all of these n equal to 2 solution, which have been claimed, or we have claimed in some previous papers, to be non-supersymmetric, but also perturbatively stable, and so far as far as we know, are also non-perturbatively stable. So they are like interesting to study. So this is just to let you know that those solutions exist. Okay, so let's go back to this n equal to 2 ADS4 solutions. We are in n equal to 8 theory, so I want to go to an n equal to 2 theory to build my black holes, but I want to keep these ADS4 solutions. So how do I do this? Well, I will do a consistent truncation, so I will truncate away some modes in a consistent manner, and this is done by selecting a group, G invariant, and I will only keep the modes which are invariant under that group. So there is a lot of work that goes into finding the right group here. In particular, this group has to be a symmetry of my full theory. So in this case, it has to be a subgroup of the gauge group times whatever global symmetry group remains in my maximal supergravity. In this case, this is like this SO6, and then there is maybe some discrete part that stays there. And this group has to keep my ADS4 solutions. It has to keep the R symmetry vector in order to put some magnetic flux on my black hole. Otherwise, I will not find the supersymmetric black holes, the PPS black holes. And I need to keep exactly 2 gravity near of the 8 I start with to have like a proper n equal to 2 theory. And if you do all of this, you realize that there is not a lot of choice that you can have. You have like basically just a Z2 times Z2 group that works. And you end up with an n equal to 2 theory with 3 vector multiplets, as in the previous cases. But you have now 4 hyper multiplets, so that's a lot of hyper that you are going to have to deal with. You have a lot of scalar fields that you are going to have to deal with, and the gauge group is now U1 squared times R squared, so you can really see like this compact and non-compact part of the gauge group. Okay, so we have built our n equal to 2 theory. That's good. We can start building black holes in them. And we have found 2 families of solution in this theory. The first one are these universal black holes, once again. So for any phi and chi solution, ADS4 solution, there is one universal black holes. They are not super interesting because they are doing exactly what you would expect. You have the right entropy for them. But importantly, there was no way to put any flavor charge to these black holes. There is a single universal black hole. There's not like families of black hole that you can play with. It's really an issue with the truncation, and if I have time, I will tell you a little bit about how we remedy this issue. Okay. So these universal black hole, you can use exceptional field theory, and you can uplift them to type 2b supergravity, as you can see here. I've uplifted them to type 2b supergravity. You don't learn a lot by doing this for the universal black holes. You can read the formulas in the paper if you are very, very interested. Okay, so we have a second families of solutions, which are, I want to call them near horizon solution, but they are not necessarily the near horizon solution of any black holes. They are just ADS2 times hyperbolic solutions. And they're interested because they look like they are scale separated. In particular, we have a 2-parameter families of solution, parameterized by these 2 numbers. So these 2 numbers actually, like, they just parameterize the upper the right-hand side of the upper complex plane. And every time you are going to reach one of these boundary of this upper quadrant, you are going to have some scale separation. So this ratio here on the right-hand side is going to go to 0, and so you are going to have somehow reverse scale separation. The ADS port is going to get very small. The H2 port is going to stay constant, if you will. Okay. And then for specific values of this lambda and gamma parameter, you go back to the near horizon limit of some universal black hole for a very specific ADS4 asymptotic. So really, you could think of those solutions as deformation of this near horizon limit. Okay, now the uplift is interesting for this scale separated solution. Why do we really want to study the uplift of this solution? First of all, we need to check that the supergravity approximation still works. So we need to check that the string coupling is still small, and we need to check that the higher curvature correction are still under control. And in this case, it's okay, everything is working great. And the second reason why we want to check the supergravity approximation, to check the uplift, is because we want to check that there is really a scale separation in 10D. So there is not like some shenanigan due to the compactification that is giving us some small scale or very big scale in 10D. So here there are some constraints, or at least we have uplifted like some smaller family of the full 2D families of solution. We've uplifted them with gamma taking a very specific value, and in this way we don't have like a wall product of ADS2 with this M8, a fibered somehow product, but we really get just a wall product of the ADS2 factor on one hand and some M8 manifold, so H2 times some circle times some S5 on the other hand. And then you can start looking at the different scales when you are going to the scale separated regime. And this is the kind of scale you get. You get ADS2 goes as 1 over cosh, but you get H2 is constant, or the volume of the S5 is going as cosh to the 5. So this is the kind of quantities that you get. So there is apparently some kind of reversed scale separation. This one is getting small, and this one is getting very big. Okay. So this is all I wanted to tell you about these solutions, this black hole solution or this scale separated solution. I just want to tell you now a little bit about some work that we hope to finish soon, which is about giving some flavor to these black holes. And to give some flavor to this black hole, I told you with the truncation that we've chosen, there was no way of giving some flavored charges to this black hole, so we need better truncation. So I call this new consistent truncation. Maybe I should have used generalized consistent truncation or something like that. But we are going we are constructing a consistent truncation of type 2B to a pure N=4 and SO4 gauge supergravity. What's nice with this consistent truncation is that there are lots of black holes that have been built here, and so we are going to be able to uplift all of them into type 2B and do the same kinds of checks on both sides of the ADS-CFT correspondence with all of these things, but now in a type 2B context. Okay, so I want to build this concentration, so I took back my slides when we went from n=8 to n=2, but this time I want to go to n=4, not n=2, so I need to keep exactly 4 gravitini, and I don't want any vector fields or any vector multiplet. So because of all of these constraints, this is too much. This group does not exist. A group that satisfies all of this does not exist. So I have to remove one of those constraints to make this group appear. I will remove this constraint, which seems to be like the most fundamental when you think about consistent truncation. I'm going to take modes which are invariant under a group which is not a symmetry group of my theory. So which is this group? This group is the one which explicitly leaves only 4 gravitini invariants. So this is the R symmetry SU8 matrix, which acts on 8 gravitini. And then it branched into an SU4 R symmetry for the 4 gravitini I keep. There is another SU4S. And I'm just going to take all the modes which are invariant under this one. It's not a symmetry because the SO6 gauge symmetry that I had is embedded diagonally here. So I'm only using this group and not the diagonal counterpart here. And if you do this and you compute all the equations and so on, you realize that you go to an N=4 theory with an SO4 gauging, no vector multiplets. which is quite surprising, and you can even show that this is actually consistent. So I'm running out of time, so I'm going to skip technical statements. But if you're familiar with generalized geometry, the point is just that the n equal to 8 embedding tensor is not SU4 invariant, but the piece which is not SU4S invariant actually decouples in the n equal to 4 theory. So we could build, so this is like the end slide. We could build using this E7 exceptional field theory and this compactification to maximal supergravity a new n equal to 4 SO4 truncation of type IIB, and so we are now working out this dictionary to finish the computation exactly. And so we will be able to uplift any solution that you have here to type IIB. That's one of the main points here. Okay. So thank you.
Okay, questions for Colin?
Hello. Presumably, so my question is about the field theory interpretation of these black hole solutions. So presumably they would correspond to taking the 3D n equals to 2 Weaver theories that you would get in the IR from these S4 configurations, and then putting them in finite temperature, right? Do you have any idea or comments on what the interpretation of this scale separation would be from that point of view in the CFT side?
Well, I think one thing which is important is that so the scale separated solution here is not like completely connected to a black hole, so we cannot necessarily make it a black hole. What we believe is correct, and it is, I don't want to set it in stone, but we think that these solutions are actually going into some CFT3, missing it slightly, and we know that this CFT3 actually can be understood as the fixed point of super Yang-Mills on a circle. So you can put super Yang-Mills on a circle, and then you can make it flow across dimension from 4 to 3 dimensions. And so we believe that these might be interpreted as some super Yang-Mills put on some, or the IR version of super Yang-Mills put on some 1, 2, 3 dimensional manifold, 4 dimensional manifold.
Then where does this scale separation?
More questions for Colin? Over there, then.
So, quick one, Colin. I think you had a last slide where you show more or less the form of the metric of this new uplift. Thank you.
I actually have a simple question. So can you go to the slide where you were talking about the uplifting of the scale separated solutions? Yeah, this one. So there you talked about checking the Sugra approximation. So what is the second inequality? I don't understand that. I mean, it doesn't make sense.
Yeah, sorry. So this is just saying that if you have like some high curvature term,
Yeah.
so this is just R. It's not like the Ricci scalar. It just means like some curvature quantity. Sorry.
Okay.
Yeah.
I see. So R is. I thought that R is radius. That's why it doesn't make sense.
No, yeah, it's not really.
Okay,
It's not really the Ricci scalar. It's just to say that I don't want to worry about higher curvature term.
Okay,
in
then
this
it makes
case.
sense. Okay, thank you.
Any more questions for Colin?
This one n equals to so the one.
So there's an also.
Yes.
Does this violate stuff that Miguel has?
What?
Like if I have an asymmetry, at least in one, I'm never going to get scale separation.
No. The statement is that with more supersymmetry, you have a tower of states united by the R symmetries. If you want to have scale separation, you should have little supersymmetry, but doesn't mean it's not the other way around. Any further questions? Right, now let's thank Colin again.